Değerli katılımcılar, sevgili arkadaşlar, bilim dostu, bilgisever, güzel insanlar. Herkese iyi akşamlar. TÜBİTAK Temel Bilimler Araştırma Enstitüsü'nün üst düzey bilimsel eylemleri giderek artan heyecanla devam etmektedir. Söylemek isterim ki bu heyecanı sizlerle paylaşmak oldukça güzeldir. Bu kapsamda bu akşam matematiksel fizik ve uygulamalı matematik seminer serimiz kapsamında bir araya gelmiş bulunmaktayız. Bu sefer kuantum mekaniğinin temellerini, yapı taşlarını konuşacağız. Ben de bu vesileyle hepinizi saygı ve sevgiyle selamlıyorum. Kuantum mekaniği isminden de göründüğü gibi kuantum düzeni tasvir etmektedir. Ve bu düzen atomik boyutlarda belirgin olarak ortaya çıkmaktadır. Kuantum düzen insanoğlu için hayal ötesi bir dünyadır. Devrimsel bir fizik teorisi olan kuantum mekaniği, bu dünyanın kurallarının anlaşılmasını mümkün kılmış, inanılmaz bilimsel ve pratik olanaklara yol açmıştır. Kuantum mekaniği, elektronu özelliklerini, atomların kararlılık durumunu ve gözlemlenen spektral çizgilerini başarıyla açıklamıştır. Maddenin atom molekül yapısında enerji düzeylerini ve moleküller arası etkileşmeleri öngörmüş ve ilgili kuralları ortaya koymuştur. Kuantum mekaniğinin uygulamaları, maddenin elektron bant yapısının özelliklerini gözler önüne sermiş, elektrik akımının kuantum muslukları olan tranzistorların devrimini gerçekleştirmiştir. Kuantum mekaniği antimaddeyi öngörmüş. Antimadde dünyada ve uzayda yapılan deneylerde gözlemlenmiştir. Bu liste oldukça uzundur. Saymakla bitecek gibi değil aslında. Kuantum mekaniğinin öngördüğü kuantum dolanıklık ve benzeri özellikli olayların günümüzde mühendislik kaynağı olarak kullanımı, insanlığı yeni bir kuantum devrimine, kuantum teknolojiler çağına hızla yaklaştırmaktadır. Özetleyecek olursak, bugün gelinen noktada kuantum mekaniğinin fiziksel dünyayı mükemmel bir hassasiyetle tasvir ettiği kanıtlanmıştır. Öte yandan kuantum mekaniğinin fiziksel, matematiksel ve felsefi temelleri de halen tartışılmaktadır. Bu akşam bunları konunun dünyaca ünlü uzmanı, son derece değerli bir bilim insanı, ABD'deki Kaliforniya Teknoloji Enstitüsü'nden Profesör Anton Kapustin'den dinleyeceğiz. Profesör Kapustin, kuantum mekaniği kesin mi konulu bir konuşma yapacaktır. Seminerimiz İngilizce olarak gerçekleştirilecektir. Dear Professor Anton Kapustin, dear participants, dear colleagues and friends, a very warm hello everyone. It is my tremendous pleasure to welcome all of you for this occasion of our Mathematical Physics and Applied Mathematics Seminar Series. TÜBİTAK Research Institute for Fundamental Sciences organizes these seminars for national and international audiences with the participation of distinguished scientists and great speakers of the world. It is also my sincere pleasure to have the honor of introducing our very special speaker, world-class expert in mathematical physics, Professor Anton Kapustin from California Institute of Technology. He is going to give a great talk under the title, Is Quantum Mechanics Exact? Anton Kapustin is a Russian-American theoretical physicist and early Anthony Professor of Theoretical Physics at the California Institute of Technology. His research interests lie in quantum field theory and string theory, and their applications to particle physics and condensed matter theory. He is the son of the famous pianist composer Nikolai Kapustin. Anton obtained his Bachelor of Science degree in physics from Moscow State University in 1993. He received his PhD in physics at the California Institute of Technology in 1997 under the supervision of John Preskill. Anton Kapustin has made several groundbreaking contributions to dualities and other aspects of quantum field theories, in particular topological field theories and supersymmetric gauge theories. With Edward Witten, he discovered deep connections between the S-duality of supersymmetric gauge theories and the geometric Langlands correspondence. In recent years, he has focused on mathematical structures in classification schemes of topological field theories and symmetry-protected topological phases. With this, I want to invite Professor Anton Kapustin to the stage to begin his talk. Anton, good morning. Thank you for joining us for this seminar. We are very honored to have you with us. Please begin your talk.
Thank you. Thank you for this very nice introduction. So it's a pleasure to speak at the seminar series. So let me start, just share the screen. So I hope everybody can see my slides.
Yeah, it's okay.
Okay.
It's perfect.
Okay, so yeah, so I must say, so I'm going to talk about some general issues in quantum mechanics, and I must warn you that I'm not an expert on this area, and that's kind of outside of my main line of research. But I thought what I'm actually doing right now is a bit too technical for this kind of seminar series, and I did think about this these other issues a few years back, so I'd like to talk about this. So what is the topic? Well, first of all, I must say that quantum mechanics is pretty old by now. It's almost 100 years old. So this is when Werner Heisenberg's paper came out, which introduced the matrix version of quantum mechanics. So soon we're going to celebrate 100th birthday of quantum mechanics. Now, so that it was created very rapidly within basically a span of 1 year by people like Heisenberg and Bohr and Jordan and Pauli, Schroedinger, Dirac. And since then it remained unchanged, even though lots of works have been written on how to interpret quantum mechanics, how to apply it, but the foundations remain the same. Now, originally, you know, the way quantum mechanics was formulated by Heisenberg and Schrödinger, that wasn't, well, especially Heisenberg, it wasn't very precise mathematically, but soon enough, by mathematics standards, the foundations of mathematical formulation of quantum mechanics have been clarified, especially by John von Neumann. This axiomatization is very, very, very important because it allows you to understand what you're really doing. Now, there are actually several axiomatizations of quantum mechanics. Von Neumann was one of the main people who thought deeply about this. And another person is Mackey, who also has another very nice axiomatization, but I'll just basically follow von Neumann. Now, so what does quantum mechanics say? Well, it's not really a theory of anything in particular. It's just a general framework for describing, framework explaining how to set up the formalism in order to develop particular models of particular quantum phenomena in the real world. So it's more like a meta theory rather than a theory. So, and it is a very peculiar theory or meta theory, not very intuitive. So even before we talk about dynamics, how things evolve with time, it looks weird. So first of all, just at any particular moment of time, we need to say what a state is of a system. So we can say, you know, how a state changes with time. We need first of all define what a state is. Now, states, according to quantum mechanics, are just vectors in Hilbert space, in complex Hilbert space. Well, not really vectors. You can, if you multiply a vector by a scalar multiple, it really gives you the same state. So more generally, one can consider density matrices. So positive Hermitian operators with unit trace. Now, these are states, and observables are also operators. They're arbitrary Hermitian operators on the Hilbert space. And possible values of some observable A are just simply eigenvalues of the corresponding operator. And finally, so given a state and some observable you want to measure, quantum mechanics tells you how to compute probabilities for observing this or that value of this observable. And this is the Born rule stated for density matrices down there. So probability of observing particular eigenvalue AI is a trace of the product of the density matrix and your projector on the ith eigen subspace. So these are the rules. And well, this is the rules on the most basic level. Now you can ask, okay, whether this theory is, whether this meta theory actually works in all possible circumstances. Well, first of all, adding relativistic invariance to the quantum mechanics turned out to be rather non-trivial, but it was solved on the physical level of rigor and sometimes even on the mathematical level of rigor. And turned out that these rules I just described don't need to be modified, really. So you need quantum mechanics and relativity combine fairly nicely. Now, well, if you really want to be, if you ask whether there is a mathematically consistent theory of relativistic physics, which also incorporates quantum mechanics, well, the answer is not really. But there are some examples of models where they've been put together and everything works. So everybody's sure there's no problem in principle, just a mathematical, some hard technical issues, which one needs to face. Now, so quantum mechanics, essentially, nothing changed in quantum mechanics, essentially, since 1926. Now, is it an exact theory? Is it the end in some sense, or is it some approximation? This is not very obvious. Well, the answer is not obvious. And lots of people thought about it. Some of them are pretty smart. For example, Albert Einstein was pretty smart, and he thought that this is not the end. So he says, well, here's a quote from Einstein, says that quantum mechanics is imposing, but an inner voice tells me that it is not yet the real thing. The theory says a lot, but does not really bring us any closer to the secret of the old one. I, at any rate, am convinced that he does not throw dice. Well, here, the old one is basically nature. That's how Einstein referred to nature, God, which identified. And so he is saying that what he doesn't like about quantum mechanics is that all it does, it predicts probabilities of this or that. That's unsatisfactory for someone who grew up learning classical physics, because classical physics predicts actual outcomes, not just probabilities of outcomes. And in classical physics, all probabilities are just outcome of ignorance. You don't know something. So that's why Einstein thought, well, if you only get probabilities out of quantum mechanics, and it means you don't know something. And so that's why he says quantum mechanics is not the real thing. So yeah, so to repeat this, so probabilities in a real world or in math, usually like just a way to talk about, like to deal with our ignorance. But in quantum mechanics, there's nothing deeper than the Born rule. Probability is built into the rules of the game. This is unsatisfactory for anyone who sort of grew up in the classical world, and actually for it's satisfactory if you believe that in the end we can learn everything. Right? So maybe in modern world where people are more accustomed to the idea, maybe cannot know everything, maybe it's okay. Now, so one obvious option is that the probability that quantum mechanics is incomplete in the following way: that probabilities arise because we really don't know something, we don't take into account all the relevant variables. So Einstein was of this opinion, David Bohm was of this opinion. So this is known as hidden variables theories, or other hidden variables belief, because it's not just a theory, just believe that there is something which we don't know, which if we knew, could explain the actual outcomes, not just their probabilities. Well, John Bell, though, sort of ruined this, in some sense, this line of thought, because he showed that if you have any theory with local hidden variables, that is where outcomes, say in Los Angeles, are determined by hidden variables also in Los Angeles, not by hidden variables in Istanbul. Well, so any such theory will badly violate some predictions of quantum mechanics. So you cannot just add local hidden variables to quantum mechanics and reproduce its predictions without probabilities. So, well, of course, you can say, well, maybe hidden variables are non-local, but that's kind of, Einstein wouldn't like that either. So there's a conflict between hidden variables and locality in quantum mechanics. And quantum mechanics predictions actually have been verified, and these Bell inequalities which Bell showed are valid in any theory with local hidden variables are violated in the real world. So, especially with the relativity thrown into the mix, that's not really acceptable. So non-local hidden variables would probably violate causality. This is not appealing. So John Bell himself, again, was not very easy, well and easy with quantum mechanics, even though he found a very important evidence that quantum mechanics is just true. He says that for me, it's a pity that Einstein's idea, that is hidden variables, does not work. The reasonable thing just does not work. But some people still continue thinking in this direction. In particular, Gerard 't Hooft is a leading proponent of the idea that quantum mechanics is not fundamental. And actually, there's a paper just like last month by 't Hooft proposing some hidden variable type theory. Now, okay, let's getting back to the original question. So, is quantum mechanics exact or not? Well, and here are some arguments against exactness of quantum mechanics. First of all, no physical theory is exact. Everything is an approximation to something. Well, second, I already mentioned, it's unsatisfactory that probabilities just come out of nothing. So where do they come from? Maybe a better theory would explain this. Now, even if you, well, a similar, well, but a bit different, more philosophical argument against quantum mechanics is that the standard Copenhagen interpretation of quantum mechanics postulates something like called the collapse of the wave function, which tells you that a measurement makes the state of the system change discontinuously. That's not very satisfactory, and many people thought about this, but there's no completely satisfactory alternative yet. And finally, quantum mechanics does not combine well with Einstein's gravity theory. Most people would think that there's some problem with gravity, but maybe there's a problem with quantum mechanics too. So nobody ever succeeded to completely reconcile the two theories. Now, that's also arguments against this. First of all, okay, there are some things which are exactly true. For example, a famous example is we know that all electrons are identical and indistinguishable because the Pauli or Fermi-Dirac statistics would not make sense otherwise. So we'll say thermodynamics is exact in the limit of infinitely large systems. Now, so now here is a bit more on this collapse of the wave function issue. So I already said that measuring changes the state of the system discontinuously by replacing the density matrix with some new density matrix, as shown here. Now, however, these words don't really explain what measurement is. So what is measurement? Should a human actually observe the system and make measurement, or just some mechanical, well, electronic device interacting with the system is enough? So this is not very clear, and it's kind of strange to say that, well, that something different, there's something different about interaction of a human with a system from the interaction of some inanimate device. So this is not really a good interpretation. Now, well, however, this is lots of people thought about this, and some people say that well, it's a really non-problem, so it's just misunderstanding. So the collapse actually does not happen, and what appears as a collapse of the wave function is simply some emergent phenomena, can be explained in terms of decoherence and interaction with between the system and the environment. Well, some people have a different viewpoint. Some people think that you actually need to modify quantum mechanics, for example, by sort of quantum gravity effects. So this is a view, well, that Roger Penrose advocated at some point. Now, going back to the last issue, how to combine, well, what are the problems combining quantum mechanics and gravity? Well, there are lots of problems there, but the most famous one is that a black hole evaporation problem. So, as Stephen Hawking showed in 1974, black holes produce thermal radiation, and the result they evaporate. Now, this is a result which uses quantum mechanics and gravity, but it's kind of a strange result because it's hard to reconcile with causality. So there's no completely satisfactory, well, until now, even despite lots of work on this, particularly using string theory, this has not really satisfactory resolution, which we will accept. Okay, so all these arguments against exactness quantum mechanics are a bit suspicious. And also pretty strong arguments, well, there's some reasonable arguments for quantum mechanics being exact. So first of all, its predictions have been verified. Everything that we do seems to come from quantum mechanics. So all of the physics is nowadays built on quantum mechanics. And on the other front, experimentally it seems to work well. But on the other hand, theorists there's some people who try to construct some modification of quantum mechanics or some generalizations of quantum mechanics. And surprisingly, there's almost nothing in that direction. So nobody ever found a sensible modification. Well, I would say that nobody managed to find a sensible modification of quantum mechanics. So now it's kind of important that these two things go hand in hand, like theoretical models which go beyond quantum mechanics and experimental tests, because testing a theory, in particular quantum mechanics, is not very easy if you don't know where to look. So I mean, a well-known a sort of philosophical viewpoint is that to test a theory, just test any predictions, and if you falsify the prediction, the theory is wrong. If you didn't falsify, then well, you're more confident that it's right, that it is right. Well, but it's not as easy as it seems, because if a theory is already successful, well, we need to know where to look for deviations, or else, well, we're just looking in the same place all the time, and we don't not find any deviations. But that doesn't really, it's not a good argument. Then, if you keep looking in one place and you always find nothing, that doesn't mean that there's nothing in a different place. So you need a theory which would tell you where to look, and for deviations of quantum mechanics of real world for quantum mechanics. That is, you need a theory which actually is different from quantum mechanics. So to test quantum mechanics, we need an alternative to quantum mechanics. Best of all, some theory with a small parameter, which reduces to quantum mechanics if we set the parameter to 0. So, and then we can make predictions using this theory. The predictions will depend on this parameter, and we could try to put maybe an upper bound on this parameter if we find no deviations between quantum mechanics and reality. That would be ideal. So then we could actually say quantum mechanics is true at the level of this accuracy or something like that. For example, well, that tests say of general relativity and along the similar lines, because there are generalizations of general relativity, and we know that some parameters, extra parameters in this other theories which go beyond general relativity must be in some range because we didn't find any deviations of deviations from general relativity predictions. But in quantum mechanics case, it's different. We don't actually have any sensible alternative with some parameter. So there are some proposals which generalize quantum mechanics, but I wouldn't say they're sensible. So I guess one of the first proposals in this direction actually came pretty late by people Girardi, Rimini, and Weber. they actually wanted to say that collapse is something which, or the wave function is not something emergent, but actually a real phenomenon. Somewhat similar to what Penrose likes. And he said that, well, this maybe they need to add something in quantum mechanics, like some tendency of the wave function to collapse to eigenstates of coordinates or something like that. That certainly goes beyond quantum mechanics. Now, Weinberg had a different proposal. Steven Weinberg proposed something called nonlinear quantum mechanics, which tries to say, well, quantum mechanics is known to be linear as far as the evolution of the wave function is concerned. So let's try to modify something, this linearity in some way. Well, I said that I don't find these proposals very satisfactory. So, for example, there's GRW proposals. As I say, proposes that wave function tends to collapse to some preferred basis, the basis where particles have positions. So this is just a kind of objective process in this theory. But this problem is kind of, this viewpoint is a bit, it's maybe okay in the non-relativistic quantum mechanics, but it's difficult to reconcile with with relativistic one. And also, that's kind of necessarily violates energy conservation. So that's not exactly satisfactory. So Weinberg's proposal, at first seems better because it seems to at least preserve energy conservation. That is actually one of his motivations. So Weinberg's proposal is to not modify what a state is. There's still vectors in Hilbert space, but modify what an observable is. So in Weinberg's modification, Hermitian operators are still observables, but there are some other observables which are not Hermitian operators. So concretely, well, suppose we fix a basis in Hilbert space, even though there's nothing that depends on the basis in this approach, which is another nice feature. Unlike a GRW proposal, which requires you to select some special basis, here there's no special basis. Anyway, so the usual observables are just the matrices in a particular basis. And Weinberg proposed to generalize this to some sum of tensors of all possible ranks. So say the usual observables have 2 indices, but then you add also other things which have 4 indices, 6 indices, and so forth. So that's what, well, that you can think of this as sort of a coefficients of a Taylor expansion of something. And the usual observables are just the leading order term. Well, so the whole goal of this was to formulate some sort of a scheme where not a theorem holds. That is, every symmetry corresponds to conserved quantity. So, for example, if your Hamiltonian is time independent, then energy is conserved. That's the whole point of this construction. However, there's also a serious problem. So in Weinberg's scheme, you don't have if you don't have an operator for an observable, then you don't know what an eigenvector or eigenvalue is. So you cannot even ask, well, you can ask, but the theory doesn't tell you what are the possible outcomes of a measurement. It only tells you it only tells you what the average of an observable is in a particular state, not probabilities. So it's actually worse than quantum mechanics in some regard. So quantum mechanics at least predicts probabilities. Weinberg's model doesn't predict that. It only predicts averages. So, for example, conservation of energy doesn't mean that energy will be conserved on the nose. It just means that the average energy is conserved. Okay, so the existing modifications of quantum mechanics are not very sensible, I would say. Well, nobody found actually a sensible modification, but perhaps we should look for them more systematically. Or maybe we can show that under some reasonable assumptions, there's no way to deform, to modify quantum mechanics. It would be a no-go theorem. Also, it would shed light on this following question, which sometimes comes up. Is it possible to combine classical quantum mechanics within some more general scheme? So can one have a consistent theory where some degrees of freedom are classical and some are quantum? That is the Planck constant universal? Because sometimes people say, for example, maybe gravity is classical So maybe you should really think of gravity as classical degrees of freedom rather than quantum one. But you still want to combine it with the quantum particles. So is it possible to do that? Now, well, there's some sort of trivial generalizations of quantum mechanics, if you think about it this way. There's something called allowing superselection sectors. So this is when you say that your Hilbert space is just a sum of Hilbert spaces, and you do not allow states which are non-trivial linear combinations of states from different sectors. And also, you do not allow operators which mix states from different sectors. So they're all sort of block diagonal in this aspect of this decomposition. So each of these Hilbert spaces is known as superselection sector. Now that goes slightly beyond quantum mechanics, as usually formulated, because you don't allow all permission operators in the Hilbert space. But it's a very mild generalization. Like, for example, people say that, say, sectors with a fixed electric charge or baryon number are superselection sectors because we do not consider operators which change baryon number or electric charge as physical. So, but it's kind of a boring generalization because, well, if some state is in a particular sector, it will stay there forever. So the label of the sector is a sort of a classical observable, but it never changes. It's not a dynamical thing. The real question is, can you actually mix classical and quantum dynamics? So that's what I mean by, question about if particle, a Planck's constant is universal. So is there a way to mix them so that both evolve, both classical and quantum degrees of freedom evolve? Now, I don't have any ideas to propose in this direction. I don't think anybody has. And so if you don't have good physical ideas, we can just try to approach it more formally. So let's use math. Well, math, there's something called deformation theory, which is basically a way of thinking, some way of thinking about possible ways to deform an existing theory within the space of all sensible theories. So, and if not, one can sometimes prove that just no deformations exist. If that's the case, one says the theory is rigid. So here's a simple example. Suppose you look at the algebra of matrices. So it's an associative algebra, and you can ask, is there some way to deform it? Well, within which world? Well, you want to deform it so that it still stays associative. Well, it turns out there's no way to do that. So there's no way to change the rules of multiplication on a matrix algebra so that the rules are slightly different, but they're still associative. So we want something like that for physical quantum mechanics, perhaps. Or maybe we'll find that there's some deformation. That will be interesting. It will be very interesting. So here's a analogy here. Well, analogy is that you can think about deforming, say, classical non-relativistic physics, say Newton's mechanics. Suppose he didn't have any physical ideas. Like Einstein, of course, discovered special relativity using physical ideas, but one could also discover it purely formally. So first you look at a group of symmetries of Galilean of Newtonian mechanics. It's called Galilean group. This is what it looks like. So Newton's mechanics is invariant under these kind of transformations, where lambda is a rotation, the matrix of rotations, and v is velocity. So we can just ask, is it possible to deform this symmetry group? Well, that's a question which can be answered pretty simply. So this six-dimensional Lie group can be deformed, and it's very easy to see that. First of all, we reformulate it as a group of all linear transformations which leave some sort of contravariant metric unchanged. This is a degenerate metric. As you can see, it has diagonal elements which are there are 3 ones and one single zero. Okay. Now that's easy to deform. Let's just consider a more general contravariant metric where the last entry on the diagonal is not 0 but some small number. It's called 1 over c squared. This action metric has an inverse. So the inverse written down there, capital G, so that's a standard Minkowski metric. well, this parameter c squared informally could be the positive or negative. So if it's a positive, then the invariance group is Lorentz group. If it's negative, then it's a rotation group SO4. But this case doesn't actually work too well. This case is sort of unphysical. But the Lorentz group case does work, and that gives you special relativity. And then once you do this deformation can verify it. The Lorentz group itself is actually rigid. You cannot deform it further within the world of Lie groups. So that's it. That's kind of the ultimate generalization in this sense. Now, of course, when you do this approach this formally, you have to you can always screw up if you just, for example, consider deformation within sort of a limited within the wrong class of objects. So I said Galilean group is made of rotations and Galilean transformations, is boosts, but why not translations too? Well, that's actually a good point. So if we look at combine Lorentz transformation and translations, we get some group called the Poincare group, which acts like this. And now we can ask, can we deform that? So if you remember, you cannot deform the Lorentz group, but you can deform this bigger Poincare group. And Poincare group is not rigid and can be deformed into these actually two options. So these are symmetry groups of de Sitter space and anti-de Sitter space. That this deformation corresponds to having a positive or negative cosmological constant. So if you sort of miss that, you would not discover curved space. But if you think about this, then you will. So there's of course a possibility of missing something because it is deforming in the wrong class of objects. Okay, so so is quantum mechanics rigid? Well, first we need to describe the set of sensible physical theories and then ask, okay, in this class, can we deform classical mechanics, quantum mechanics? Now, what is a sensible physical theory? Well, it's kind of a debatable question, but as a minimum, we want both classical mechanics and quantum mechanics to be sensible. And also you want quantum mechanics to be a deformation of the classical one. That puts some constraint okay, so let's recall actually how in what sense quantum mechanics is a deformation of the classical mechanics, because at first sight they look very, very different. Well, in classical mechanics, you start with a phase space. So it's some manifold and symplectic structure, some non-degenerate two-form, closed two-form. Observables are real-valued functions. States are just points on this phase space. And finally, the evolution is given by Hamilton equations written down below. This one. Okay, that looks very different from quantum mechanics because there the basic object is totally different. Start with a Hilbert space. And then you have observables, which are Hermitian operators, and states are rays or density matrices on this Hilbert space. Well, the only thing which looks similar is the evolution. The evolution looks kind of similar because you have some sort of bracket. Instead of Poisson bracket, you have a Lie bracket on observables. Okay, so how do we reformulate everything so that classical mechanics and quantum mechanics looks more similar? Is the first question. Well, okay, so a good place to start is to say that there's in both cases, there's a Lie bracket on observables, Poisson bracket or commutator. And there is a good physical reason for that, not just math. Because if your dynamics is formally in terms of the Lie bracket, then you automatically get Noether theorem, which states that conserved quantities are related to symmetries. This principle is true both in quantum mechanics and classical mechanics. And basically, equivalent way to state it is that observables are also things which generate infinitesimal symmetries of the system. And when you have any notion of infinitesimal symmetry, it leads you to a Lie algebra. So that's why observables form a Lie algebra. So that's true both for classical and quantum mechanics. Now, so it's good to that seems like a reasonable principle in general. However, two things which is still difficult to reconcile, and namely the fact that you have complex numbers in quantum mechanics, and then no complex numbers in classical mechanics. So that's one big difference. Second, also we represent observables in quantum mechanics by Hermitian operators. That looks totally different from what you have in classical physics. So how do we make these things more similar? Now, there's also an issue of states, but I think this is actually a good way to think about states, well, if you understand observables, because this is actually a good answer. So the only sensible way to define probability, according to a theorem of Gleason, is by the Born rule. So I'm not going to explain that, but basically, let me skip that in the absence of time. But it basically says that this Born rule is the only way to formulate, to define some way of defining probabilities of outcomes, if you believe that observables are Hermitian operators. So let's forget about states, therefore, because once we figure out why observables are given by Hermitian operators, we already sort of know how to derive Born rule. Okay, so let's go back. So observables in classical mechanics form a real vector space. So, and that's very sensible because, again, first of all, they expect them to be Lie algebra, and any Lie algebra is a vector space. Also, if they can multiply observables, that's also reasonable. If you measure one observable, another observable, can multiply them and get a third one. This operation is associative and commutative. Mathematically, you say that observables in classical mechanics form a commutative algebra over real numbers. And finally, there's also this Lie bracket, which satisfies the Leibniz rule as far as multiplication is concerned. So it's a very reasonable thing too, because if you think of observables as generating infinitesimal symmetries. Now, so the difference between Hermitian operators, in classical mechanics, observables are very striking. First of all, they do not form an algebra, at least not in any associative sense. If you take two Hermitian operators, their product is not necessarily Hermitian. Well, that's actually fairly reasonable, because multiplication of complex operators actually does not have a physical meaning, because complex operators don't have a physical meaning. Only Hermitian ones do. So physically, maybe it's okay, but mathematically, we do use operators. So it's a bit strange. Why do we, like, operators are natural if you think about complex operators, but if you think about Hermitian ones, they're not very natural. So, and people, especially Jordan, was bothered by this. So Pascal Jordan, one of the founders of quantum mechanics, he said, well, maybe we should, multiplication of Hermitian operators doesn't make any sense, because you get something which is not Hermitian, and therefore not an observable. But let's look at the anti-commutator. Maybe that has a physical meaning. Now, here's another trouble. This operation is commutative, but not associative. There's some modified condition, which you just see on the bottom, which is weaker than associativity. That's known as the Jordan identity. So, since then, a real vector space with some weird commutative multiplication quotes satisfying this identity is known as a Jordan algebra. Now, physically, though, this is maybe nice mathematically, but physically, this multiplication doesn't have much meaning either. Why should we care about this weird non-associative product? Well, Jordan said, really, it's not even the most basic operation. The basic operation is squaring an observable. And if you know the square an observable, then you can also figure out this weird product simply because of this identity. If you know how to square, you can also deduce some bilinear operation called A circle B. Okay, maybe, but that doesn't explain why this Jordan identity should be satisfied. So why is squaring an important thing? Well, because if you know how to define square, you can also figure out how to find arbitrary powers, just like recursively. Now, well, that's kind of good. That's good, but so we certainly want this property that multiplying a to the power n and a to the power m is the same as a to the power n plus m. And then, of course, once you have the powers, you can define polynomial functions of observables, which is nice. Now, this is good. It's all good, but actually, Jordan identity is much stronger than this, or it seems much stronger than this. So all we want is this powers to be correctly defined. Why should we? But that's that follows from the Jordan identity. But why would you want Jordan identity? Well, Jordan thought about this and has this paper with a very long title where he proves the following mathematical theorem. He says that if the squaring is in addition formally real, it's some strange property, then Jordan identity actually is required, is also necessary, not just sufficient. So what is formally real? Well, it means that you have a sum of observables. If you look at several observables and the sum of squares is 0, that implies that each of them, each square is 0. Sorry. Well, so here this is a theorem which says that if you, so this is a theorem again. So if you have of Jordan, that if you can define polynomial functions of observables and the squaring is formally real, then your set of observables is actually a Jordan algebra. Well, is it a satisfactory answer? Well, let me just skip this. Some people thought it is, and started looking at classification of formally real Jordan algebras. If you look at finite dimensional ones, one finds that there are 4 infinite families, but they're not really. So first of all, of course, there are real matrices, and there are complex matrices, and the quadratic matrices, and then there's some other weird one coming for Dirac gamma matrices, and then finally there is some exceptional one related to octonions. So this can be classified, but that's not exactly satisfactory either. So first of all, we have 5 cases, and nature uses only one of them. Now, second, this formally real condition looks natural, but actually is not. So if you have 2 non-commuting observable, then a squared plus b squared has nothing to do with a or b. It's just totally different setup needed to measure measure a squared plus b squared. So there's no reason to expect for this formally a real property. Well, what are alternatives? So Jordan's approach then does not really didn't satisfy anyone in the end. However, there's another approach which is less well known, which I think is much more satisfactory. So the basic idea of Jordan is correct. That is, I think that one needs to regard squaring and the Lie bracket as the basic operations. So because they're defined both for quantum mechanics and classical mechanics, so it's natural to take them as necessary in general. So we just need to understand why sometimes this multiplication, the square, well, which comes from the squaring operation, is associative, but for quantum mechanics it is not. Okay, so here comes the interesting additional principle, which due to Niels Bohr. So he said, a requirement of composability, that if you have 2 physical systems and their sets of observables, then there's a way to form should be a way to form a composite system. And observables for the composite should include products or observables of subsystems. So I don't know when Bohr proposed this, but he didn't really pursue it, but his assistant, Peterson, and another guy named Gurgin took this up. And an interesting paper, little known, from '76, which says the following. So suppose you have a set of observables for each physical system, it's for each physical system is some real vector space with 2 bilinear operations. We call them A circle B and commutator. So the bilinear operation, the symmetric one, and the skew symmetric one. And suppose when we form a composite system, the spaces of observables simply tensored together, like in quantum mechanics or classical mechanics, which in both cases is true. And the bilinear combination, bilinear operations for the composite system are just linear combinations of products of bilinear operations for the subsystems. Then Gurgin and Peterson showed that the 2 operations are related. There is a real number, universal for all systems, such that the failure of the symmetric guy to be associative is related to the double commutator. So that's the equation on the bottom. So what is this? That looks interesting. So two things now suddenly get related. We consider both of them. So in Jordan case, they're totally unrelated. Turns out that the case when this number is 0 is the case of classical mechanics, because if you look back, if it's 0, then it just means that the squaring, well, this symmetric operation is actually also commutative. And sorry, is associative. Sorry, not commutative. It's already commutative, but it is associative. So you get associative algebra, and then actually also true that they get actually something in classical mechanics. It's called the Poisson algebra. And the case when this number is positive turns out to be the case of quantum mechanics, because then what this identity actually says, for if this number is bigger than 0, you can just call it h bar squared, and then it shows that the identity is equivalent to saying that the symmetric and skew-symmetric product are just anti-commutator and commutator up to a factor of I. So the case, and then there's also a case where this number is negative, but then Planck constant comes out basically purely imaginary in a sense. So that's a very nice result. So this theorem actually also explains where complex numbers come from. They come when we rewrite the properties of real operations, like symmetric and skew-symmetric operation, in terms of more familiar associative product. If this number lambda is positive, you need complex numbers to rewrite, but it's purely like just a trick. This theorem also explains why h bar is the same for all systems, because this number lambda is the same for all systems. Now, there is some like a technical issue. Well, just saying that observables are associative algebra just means that they're matrix algebras. And also there is a loophole that you need to explain why negative lambda, that is imaginary h bar, is not okay. Well, in some conditions of the conditions of this theorem are not exactly physical, but it's easy to improve. So here's a synthesis of all these approaches. First of all, you postulate that observables form a Lie algebra, a real Lie algebra. There's a squaring operation, and when forming composite system, there should be some way to multiply observables of the subsystems. And final principle, which I didn't have, but I'd like to add, if you have a composite system, then as far as a system AB, and as far as A is concerned, observables be just like ordinary numbers. So that's a very natural principle too. So for example, commutator of A1B and A2B is simply commutator of A1 and A2 times B squared. So one can actually then rephrase this Gurgin-Peterson theorem as follows, that this theorem can be stated as follows, that with these assumptions, the set of observables must be an associative algebra. And this implies that quantum mechanics is rigid, at least in the finite dimensional case. Because you see, if you manage to deform the data of your theory, then you should also deform the associative multiplication. But we know that algebra of matrices are rigid, they cannot be deformed. Therefore, you cannot deform the rules. So this is actually a no-go theorem. It says that finite dimensional quantum mechanics cannot be modified without violating our physical requirements. And the physical requirements are like the Noether theorem and the ability to form composite systems. And one can actually even argue with some further requirements that this Planck constant actually must be real and non-zero. And therefore, the algebra of observables must be a sum of matrix algebras. So I'll skip that part. So what are the conclusions of all this? Well, if you believe these assumptions, then quantum mechanics seems like an exact theory of nature, at least for finite dimensional systems. Now, it also sort of now understand why complex numbers are needed, because basically it's some sort of formal trick for restating the structures in a familiar form. You just need to take square root at some point of a negative number. Also now, so this theorem also shows that h bar is universal, and so you cannot like put together classical and quantum systems because if you fix non-zero h bar, you're completely quantum. there's no nice way to mix classical and quantum dynamics. So in general, you could say that, well, what the theorem really shows that if you want to modify quantum mechanics, you either will have to violate Noether theorem or do some other violence, like destroy probabilistic interpretation. Okay, that seems pretty strong result, but of course, as usual, there are loopholes. First of all, maybe infinite dimensional systems, because this rigidity I mentioned is really holds true only for finite dimensional systems. But that's not particularly interesting loophole, because you would think that any infinite system can be approximated by finite ones. A more important loophole, I think, is that that this Noether theorem sort of assumes implicitly that time is fundamental. But if time is not fundamental but emergent, then maybe Noether theorem is also maybe too much to ask. So that's, I think, the main loophole in this. So that's where we are. So I tend to think that quantum mechanics is exact unless time is emergent, which is actually very likely, given what we know about quantum gravity. So maybe in the end, quantum mechanics will found to be not exact, but then if we understood how to do that, we'll probably also need to understand how to incorporate gravity and make time emergent. Okay, I'll stop here.
Anton, thank you so much for this very deep and exciting talk. That was a pleasure to listen. Thank you. So now we can pass to questions and take questions through the chat button of Zoom platform or just by raising hand or asking. Anton, can we take several questions or a couple of questions?
Yeah.
May I ask about the passage from quantum to classical regime? For example, in cosmology, as you know, in early universe, it turns out that the fundamental things in vacuum fluctuation, quantum fluctuation, and then emerges classical matter, galaxies, and so on. So passage from classical to quantum still, from quantum to classical remains mysterious. How can you comment this in sense, in terms of rigid things that you formulated here?
Well, yeah. So of course, so I really only understand this in the context of this finite dimensional systems, which are much easier. But roughly speaking, so the usual procedure is to treat quantum. Well, certainly when you pass to classical dynamics, you usually focus on some classical, some subset of variables which are evolve much slower than the rest of the variables. Mm-hmm. And the rest you sort of, and you at first approximation just treat them as fixed. So, and then the rest you treat using quantum mechanics and treat this slow degrees of freedom as just parameters. And once you solve the problems for fixed values of these parameters, then you sort of now start worrying about dynamics with the slow ones. I guess, and for them you write the classical dynamics. So I guess the main message of this, well, one of the messages of this approach that I explained is that you cannot actually make this into exact rather than approximate scheme. So this is all happens all in some limit where, the first approximation just say, the classical slow variables just don't evolve at all. And then once you solve the quantum problem, you go back and, so now actually they do evolve. So this only makes sense in some limit. And if you try to say that, well, can I somehow just have classical and quantum in one theory before taking the limit, that's not gonna work, not approximately, but exactly, that doesn't seem to work.
Thank you. More questions, please. So foundations of quantum mechanics and problem here for more than 80 years are discussed some controversial opinion and so on, so on. So it seems to be that it still will continue, yes, Anton?
Yeah, well, I would say that most of the controversy in the arguments continue about interpretations of quantum mechanics.
Yeah.
That's where most of the work was, and it's very important and interesting question that's still unresolved. So I decided not to talk about it, essentially. I only mentioned this in passing, because there's nothing there which is going to be resolved anytime soon, I think.
Mm.
But the question of whether one can actually change the rules a little bit, which in a sensible way, it's something which I think is easier to answer. And that's what I tried to explain.
But another thing, which is deeply philosophical also, usually very active in discussions, fundamental nature of time, whether it is fundamental or emergent. What is the modern point of view, in scientific point of view, I mean, not philosophical in this sense?
Oh, I think it's right now there's no like really, I wouldn't say there is a well-defined proposals of any kind which explain in what sense time could be emergent. I mean, there are some attempts, but it's still more a philosophical issue than a physical one. Like, there are some attempts like by Alain Kohn in particular, the French mathematician, but he approaches more from a mathematical viewpoint. So I'm not really sure. I don't think there's a sensible physical attempt to explain what emergent time would even mean.
Mm-hmm. Yes, that's true. I agree. Yeah,
it's a fun subject to think about, though.
Yeah, that's true. That's true. Some people thank you for this talk. Please ask questions. Mm-hmm. So if no more questions, so our people here is very shy indeed to ask questions. So there's one question, I think. Anton, can you read these questions if you found it is interesting?
Well, I guess, yeah, so I see the question. Yeah, so I guess we're talking about emergent versus fundamental time. I guess somehow, I think maybe it was Dirac who said it, or maybe someone else, but basically, unless you have a theory, you cannot really test anything. So the theory tells you what's observable and what's not. So in order to test the nature of time, first you need to have any theory, maybe even the wrong theory of time, and then you might be able to reject it or confirm it, or most likely reject it. But since we don't have anything, there's nothing to test really. We don't know where to look. It's like testing a theory. Like, could it be that black and white are really the same thing? Like, since if there's no theory, maybe it is, but if there's no theory, you don't know where to look to test this.
Yeah, exactly. So, more questions, please. So, if no more questions, Anton, perhaps we can stop here and close our section. So it was very pleasure to listen to you. Thank you once again for this nice talk. So we will be very happy and thrilled to have you here in person in the framework of our summer schools or workshops or seminars when this pandemic disaster finally leaves the world. So will you please make final remarks if you want?
No, it's good. I'm said what I want to say. So.
Yeah. So for the time being, maybe goodbye. Take care of you. Thank you once again.